All right, so we solved these three equilibria simultaneously. Is going to be very difficult, right? That's going to be difficult. So obviously somebody's going to write some kind of computer program for this, right? Which somebody did. We're going to use it in lab, Visual MinTech.
Isn't for the top one watch forecast?
Oh,
I forgot to.
yeah. Oh, yeah. That's right. Made it the same. This is H2PO4. This is hydroxide. Thanks. Yeah, that's right. Difficult, but have you ever heard of engineering equations? Engineering equations is you take all these equations that you get from whatever, and then you just try to simplify them. You do they care about all these numbers, all those numbers? No, you just want to plug in one number and get the answer, right? That would be like an engineering equation. And so the same thing here. Difficult, and so we make some assumptions here, and then the assumptions would be, fairly high concentration and SA. And then what we get is an engineering equation for this. And the engineering equation for this is going to look like this. The pH is going to equal 1/2. Actually, let's write it like the book does. It's going to be the pKa for the amphoteric. Amphoteric is, the Ka and Kb, plus the pKa for its conjugate acid of the amphoteric. So conjugate acid divided by 2. So we aren't actually going to figure out the inventory of this. We're just going to do this. And so actually this problem is not that difficult. And so what it's going to be is it's going to be the pKa for H2PO4 minus. Plus the pKa for, what is the conjugate acid of H2PO4 minus? H3PO4 divided by 2. And so all we have to do is calculate the pKa. Well, the pKa is just the negative log of the Ka. And so the Ka for H2PO4 minus was what again? Erased it. I know the number already. It's 7.20 is the Ka for that, plus the pKa for H3PO4. I should have opened the book here, but it would be in the polyprotic acid line. Appendix D. Or can somebody just calculate it? The negative log of 7.1 times 10 to the minus 3. Okay, 2.15. 2.15 is what's in the book, so we'll just use that. So this comes out to 5.05 divided by 2. This is a 2.525. I'm sorry? You get? Oh, shoot.
Uh-oh.
9.35 divided by 2.
4.675.
Okay. 4.675. So at least we aren't going to do the inventory calculation for a solution like sodium dihydrogen phosphate or any other amphoteric because it requires simultaneous of at least 3 equilibria. It's too much. Okay. Instead, we're going to use this equation. This equation is in chapter 17, but it fits because we're talking about how to deal with it. Because acid solutions, you look at Ka. Base solutions, you look for
KB.
Amphoterics, you have to do both, Ka and Kb, which means we're going to use this equation, right? Because amphoterics, you got to do both. Okay? Well,
Excuse me. The water is amphoteric too.
What?
The water is amphoteric too.
Amphoterics go both ways.
Water could act as an acid and a base.
For example, this is an acid. This only goes one way. But this generates an amphoteric. But the amphoteric that's generated has one of the K's, like Kb, already compensated for in the previous step, right?
Mm-hmm.
So we don't have to worry about it. And so acids, we always do Kas. Bases, we always do Kbs. And that's it. We don't worry about all the others. But the only exception is amphoterics. Amphoterics alone are going to be difficult. All right, that's chapter 16. Basically, in a nutshell. Except the only thing is structure and reactivity and ions. And so let's talk about salt solutions and pH briefly. The cations of the soluble hydroxide, these are salt solutions. Are neutral. This is sodium, potassium, magnesium, calcium. Actually,
Excuse me.
not magnesium. Calcium,
Ooh.
strontium, barium. Magnesium is pretty much neutral too. Others are acidic. So let's talk about some other cations that are quite acidic, like this. Aluminum 3 plus. If we look at the Ka for this is aluminum 3 plus A cubed. The Ka for aluminum 3 plus A cubed is actually kind of big. Oh, 10 to the minus 5. I don't have the full number. We'll go to iron 3 plus then. Iron 3 plus or iron 3 plus? Iron 3 plus. Ka is 10 to the minus 5, which means it's about as acidic as acetic acid, right? That's pretty big. Iron 3 plus is even bigger. Iron 3 plus has a Ka, and so iron 3 plus's Ka is 6.0 times 10 to the minus. Can somebody read that? 3. That's 3. Which means it's about 100 times more acidic than acetic acid. And so why is it so acidic? Why these are so acidic is because of the structure of these. And so if we look at the structure of something like this, it's actually a hexaoqual complex. 3 plus. And what happens is it makes the hydrogen on water considerably more acidic due to the inductive effect, or whatever you want to call it. That is, we have a 3+ on the iron, and that 3+ on the iron is going to withdraw electron density from oxygen. And so if oxygen is becoming less and less electron rich, it's going to suck even more electron density off the hydrogens, and it's going to generate a fairly large partial positive charge on that, making this very attractive to bases. And so a base comes along, it's going to see that, like hydroxide or water. Let's just bring a water. Water is amphoteric, it goes either way. And so water comes along. What? If water is amphoteric, do we have to use that funny formula?
Yeah.
No, we don't. Water is amphoteric, but we don't have to use that funny formula. Why? Yeah, we know the pH, but it's a simple reason why. The reason why is, you know what KW is? KW is Ka and Kb together. Because Ka is hydrolysis to form hydronium. Ka is. Kb is hydrolysis to form hydroxide. Kw does both. And so it's Ka and Kb are incorporated into one equation. And therefore, we don't have multiple equilibria that we have to deal with. So water is unusual. But anyway, this is going to attack that, right? This is going to be a much more attractive proton than a normal proton in water. And so it makes it considerably more acidic. In fact, this is a polyprotic acid. There's actually a Ka1, a Ka2, a Ka3. Well, 6, then you get into hexahydroxo, but that would be too much negative charge probably. So for sure, it's a K1 through K3 because you end up with forming iron 3 hydroxide. And so anyway, Ka1 is going to be the biggest. And so here, this is going to go to Fe, and this is going to be converted into a hydroxo ligand. And this will be hydronium.
So notice acid-base reaction.
Oh, Bronsted. This is 3+, but the ligand here is minus.
You're mentioning about ligands.
What?
You're mentioning about ligands.
Yeah. Because the hexaqua complex has 6 aqua ligands. So do you see how iron 3 can act as an acid here? Same thing with aluminum. It's usually the higher charge ones are going to be more acidic, and so we tend not to worry about this so much, right? All right, the next thing is the anions of the strong acids. Anions of strong acids are neutral. Except for H2SO4. And so this would be like chloride. The anions of strong acids would be the conjugate bases. These are the conjugate bases. Chloride, bromide, nitrate. The thing about HSO4 minus, HSO4 minus is pretty much neutral as far as base properties, but it's an acid. It's a decent acid. So this is acidic.
Wouldn't acetate be an exception?
No, because acetate is not the anion of a strong acid. Acetate is the anion of a weak acid, acetic acid. And so acetate would be basic. So we look at salt solutions in the same way. We just look at how they hydrolyze water. And so examples of this would be like this. Example would be FeCl3. You know, Fe3 plus is Ka. Cl minus is so weak, we just call it neutral. We completely ignore it, right? And so here we'd be doing Ka calculations. Next example would be sodium acetate. Acetate is the anion of a weak acid, and so sodium ions are neutral, right? Acetate ions are basic, and so we do Kb. Then we have things like this. Ammonium acetate. Ammonium is Ka. Acetate is Kb. So what do we do?
Should we do both?
We should do both, right? We got to do both. We got to do Ka and Kb.
Then we got to solve it simultaneously.
Yes, because Ka and Kb are going to be tied together by
Water.
Kw. And so unfortunately, this is simultaneous. There's no engineering equation for this. The only reason why an engineering equation worked for amphoteric is because the acid and the base were the same species. Here, the acid and base are two totally different species, which means we don't have this. This is not going to work. pH is, you know, that doesn't work. pH equals pKa. This must be solved simultaneous, which is difficult. And so all we do here is we do qualitative. Therefore, when we have a simultaneous situation like this, then the best we can do is qualitative. And so what we do is do this. If Ka is bigger than Kb, then we say it's going to be acidic. If Ka is comparable to Kb, then it's close to neutral. We say about neutral. And then, of course, if Kb is bigger, then we say we're going to generate more hydroxide, so it's going to be basic. And so we aren't actually going to calculate any numbers. We're just going to say it's, you know, it should be acidic, it should be neutral, or it should be basic, because the actual calculation is too difficult for us. But we have software that can do that, which we're going to use later on. And so, so this is one in next week's lab. In next week's lab, we're going to do a potassium aluminum sulfate. Is that right? Yeah. And what was the ratio? I think this was two sulfates, one aluminum. What is this? This is -4. Yeah, maybe it was like this, potassium aluminum sulfate. And so what we have here is potassium ions are neutral. Aluminum is acidic, so that's Ka. Sulfate is basic, it's Kb. Because sulfate is the conjugate base of hydrogen sulfate ion. Hydrogen sulfate ion is a weak acid. And so that's why Kb is significant here. It's not neutral. Sulfate's not the anion of sulfuric acid. The anion of sulfuric acid is HSO4-. This would be the anion of HSO4-. And so, unfortunately, this is simultaneous, right? And so, for this one, we're just going to determine, you know, is it acidic, basic, or close to neutral?
Excuse me, now why is sulfate a base?
Why is sulfate a base?
Like, why is it like basic?
Okay, this is the other way of remembering this. The stronger the acid, the weaker its conjugate base. And so if you have a very strong acid, the conjugate bases are so weak, we consider them neutral. So for example, HCl is a very strong acid. Its conjugate base is chloride. Chloride is so weak, we consider it neutral. But sulfate is not the conjugate base of a strong acid. Sulfate is the conjugate base of a weak acid. And so the conjugate pairs would be HSO4 minus and SO4 2 minus. This is the base, this is the acid. Is that a strong acid? No, it's a weak acid. Therefore, it's going to have a moderately strong base. And so sulfate is actually a decent base. That's the reason why.
Okay.
All right, we'll stop here.